Hi and welcome to video 1 of Unit 4 Topic 1 of the Math Methods curriculum, and we're looking at the second derivative and motion in this video. Now I just want to make really clear that not only for the second derivative and motion, but just for this whole topic, that the concept of this topic is about the second derivative. So you've done kinematics before, you've done motion before in math methods, and you've moved between displacement and acceleration with velocity in between before. This specifically looks at deriving to get to acceleration. It does not consider moving backwards. Although moving backwards is obviously integration, and you've done integration in Unit 3, so therefore it is fair game on your external exam. Just be aware it's not fair game in this topic, the way that it's set out. But anyway, let's have a look at the second derivative of motion. So the second derivative, hopefully you recall that if we start with y equals f of x, then when we derive y, we get f dash of x. That's our derivative. And when we do the second derivative of that, we get d squared y dx squared, which is f double dash of x. That's our notational stuff, and hopefully you've seen and you understand that. Now, what's it useful for? This topic will cover all of these areas. Acceleration, first of all. If displacement is equal to x, then we get x double dot, which is a physics notation for acceleration, sometimes used, is equal to d squared x dx to t squared, or x double dash of t. So that's our representation for acceleration. We can also use it to test the nature of a stationary point. So if we know we have a stationary point, then if d squared y dx squared is less than 0, we get a maximum. If d squared y dx squared is greater than 0, we get a minimum. You've seen this before. And of course, we can also look at a point of inflection. So if d squared y dx squared equals 0, then this is a point of inflection, or a point of inflection exists, and we can do what we need to do for that. But the point of inflection stuff in particular is a little bit funny. There's some other little elements to that which we will get to as we move forward. Now, if dy dx equals 0 and d squared y dx squared equals 0, then this is considered a stationary point of inflection, which in my class I invented a song for. Not a very good song, but a song nonetheless. So let's have a look at some examples. For the function y equals x squared e to the negative x, determine when d squared y dx squared equals 0. So the first thing we need to do is derive it. And so when I derive it once, I get dy dx, I'll just zoom in a bit here, is equal to, now this is a a u-v type question. I'm going to skip over the really basic differential parts, and hopefully you understand that, but just stop the video and check it out yourself if you need to. So I've got u dash v, now u dash is 2x and v is e to the negative x, plus v dash u, and so v dash is negative e to the negative x times x squared, and so this becomes 2x e to the negative x minus x squared e to the negative x. And then the second derivative, d squared y dx squared, is equal to, again, I've got this uv and uv situation here. I've done the second one already because that was my original y, so I can deal with that quite easily. But the first one's a bit trickier. U dash v becomes 2 e to the negative x, and then v dash u becomes plus negative e to the negative x times 2x. And then minus, and inside of this I get the same thing I got for dy dx, which is 2x e to the negative x minus x squared e to the negative x. And then I can simplify this to become 2 e to the negative x minus 2x e to the negative x minus 2x e to the negative x becomes minus 4x e to the negative x. And then negative of a negative becomes a positive, x squared e to the negative x there. And I'm going to take out the common factor, e to the negative x, and I'm left with, and I'm going to reverse the order of my terms here to make it look more like a quadratic, but I'm left with x squared minus 4x plus 2. And I want to know, when does d squared y dx squared equal 0? And so I want to know, I'll use the null factor theorem here, when does e to the negative x equal 0, or x squared minus 4x plus 2 equals 0. And this never happens because it's an exponential, even though it's a decaying exponential. Put in a really massive x there and it still doesn't quite equal 0. But over here I get x equals, and they're not nice numbers, but you could do this in your calculator, or you could use the quadratic formula, 0.59 or 3.41 as my x values. So those two locations are where d squared y dx squared equals 0, which means that I have a point of inflection at those two locations. Now let's have a look at a second example. Example 2. If the tidal height in a bay moves according to the rule ht equals 0.7 plus 1.1 cos of pi on 6 x minus 3, determine when its acceleration is the greatest. So this is a kinematics type question. So ht equals that, therefore the velocity is equal to h dash t, which in this case is equal to the 0.7 disappears. I get 1.1 times cos goes to sine, but remember it becomes negative, and then pi on 6 x minus 3, but I have to multiply by the derivative of the inside function, which is pi on 6 x minus 3, and I've written derivative as d. See what's happening here. So I'm going to leave it as d to t. This should probably say t, because I'm doing it as with respect to time. So let's remove this as well, and we'll call that t also. Oh, and this guy. There we go. So that's my velocity with respect to t. And now that I've determined my velocity almost, I just need to finish it off. Pi on 6 comes out as the derivative of that term. I get negative 1.1 times pi on 6, and then sine of all this stuff. Pi on 6 t minus 3. I'm going to write it down as negative, now 1.1 pi on 6. I don't really like decimals in fractions, so I'm going to write it down as negative 11 pi on 60 sine pi on 6 t minus 3, and I can't simplify that. So that's Vt. Now I need to determine my my acceleration, and my acceleration is equal to h double dash or v dash t, which in this case the constant terms disappeared. And following the same principle, I've got negative 11 pi on 60 cos, and it doesn't change the polarity, so it doesn't change the negativity of this term, t minus 3, and then I have to multiply by the derivative of the inside again, which is pi on 6 again, and that gives me negative 11 pi squared on 360 cos pi on 6 t minus 3. And I want to know, when is the acceleration the greatest? Now, I could go through this whole process here and determine when the acceleration is greatest by doing another derivative and looking for the stationary point of my acceleration function, which would work. So I'll let the next derivative equal 0. But here's a little trick to do with periodic functions. Cosine of anything is between negative 1, negative 1 cos of that stuff and 1. So if I'm looking for when is this the greatest, I'm thinking, well, which of these values between negative 1 and 1 is going to make this a maximum, the greatest? And in this case, I can see now, ordinarily it would be 1. Often you'd look straight to the 1. That's the greatest value that cos of something can take. But because this is negative, I'm actually going to use that negative 1. So the greatest that this can be is when cos is equal to negative 1. And therefore the greatest is 11 pi squared over 360. And so I'm going to say when cos pi on 6 t minus 3 equals negative 1. So that's an approach you can take as well, and I've already proven that it's the greatest, but just be careful about what the question's asking. If it's asking you to do it using stationary points or the first derivative, then probably avoid that. So there's a couple of examples of how we might apply the second derivative and what it means. All the best.